Okay, hello everyone and welcome to the European Non-Associative Algebra seminar. Today I'm glad to introduce Carla Rizzo from the University of Coimbra, Portugal, and she's going to talk on differential identities of matrix algebras and related growth problems. Please.
Thank you very much. Thank you very much for the invitation. So yes, today the talk is focused on in the area of polynomial identities. And in particular, we're going to talk about differential identity. There are particular polynomial identities. So to start, first of all, we have to understand what are identities in algebraic array structure. So the concept of identity is really general, and even the basic law we learn at school are identities, like commutative law, distributive law, and so on. But in general, identity is a symbolic expression involving some operation and variable, which is identical satisfied when the variable is substituted in a given algebraic structure. So to talk about identities, first of all, we have to understand which are the algebraic structure we are interested, and then we have to understand which kind of symbolic expression we want to use. In PI theory, the theory of polynomial identities, we mostly focus the symbolic expression are type of polynomials, and in specific in this talk, the algebraic structure is going to be are going to be algebras with derivation. So to start, I'm going to start first to explain what are algebras with derivation, and then we're going to talk about the polynomial identities in this kind of structure. To talk about algebra with derivation, I will recall what are the derivation of an algebra. So first of all, for me, from now on, F is going to be always a field of characteristic 0. And then if we consider an algebra over F, then a derivation, of course, is a linear map that satisfies the Leibniz rule. So an example for associative algebras, a really general example for associative algebra are the so-called inner derivation that are actually, basically, it's the adjoint map induced by an element A of A, that are actually the commutator. The adjoint of A applied to an element B is the commutator between B and A. A property, really interesting property of derivation is that if you consider the set of all derivation of an algebra, this set has a structure, really a strong structure, because it's a Lie algebra with respect to this operation. In here, the composition are basically if it because we know that if we do the composition to the derivation, it's not in general anymore a derivation, but if we do the commutator of two derivation, it's still a derivation. Okay, so a sample of derivation. If we consider matrix algebra, because my talk is gonna, the focus of my talk is gonna be also matrix algebra. So I'm gonna talk a lot of matrix algebras. So if we consider the algebra of K times K matrices over F, we know that as a consequence of the Nether's column theorem, that any derivation of MK is inner. And also we have that the algebra of derivation of MK is actually isomorphic to the special linear Lie algebra of order K. In case K is equal to 2, I'm going to denote the basis. I'm going to choose as basis for my Lie algebra of derivation the basis denoted by E, F, and H, where E is going to be the adjoint of E1, 2, F the adjoint of E2, 1, and H the adjoint to E1, 1 minus E2, 2. And then, of course, this algebra is isomorphic to SL2. If we consider another type of matrix algebras, they are hypertriangular matrices over F of order K. Then again, we can prove that any derivation UK is inner. We have to notice that for matrices are simple algebras, and then any semi-simple algebras as inner derivation, but UK is not in general is not a semi-simple algebra. It has a it has a Jacobson radical. And so, but in this case, we have again that any derivation is in, and we have something more, that the Lie algebra of derivation UK is a solvable Lie algebra. If we consider UT2, then we are going to denote this is the algebra of derivation is a Metelbelian Lie algebras, and we are going to denote the basis of this algebra. I'm going to choose as basis of this algebra, the basis epsilon delta, where epsilon is the adjoint of E22 and delta is the adjoint to E12. So, to actually talk about algebra with derivation, we have to do a step further. We need something more because, as I said before, composition derivation is not a derivation. For this reason, we have to consider a universal object that is the universal enveloping algebra of a Lie algebra. So if I consider a Lie algebra L, then I can define the universal enveloping algebra of L, that is an associative algebra with unit that satisfy this universal property. This algebra, for any given Lie algebra, L exists a unique up to isomorphism universal enveloping algebra. A really nice way to describe a universal enveloping algebra and basis of universal enveloping algebra is given from by the theorem of Poincare-Birkhoff-Witt. So if we consider our Lie algebra L, it's universal enveloping algebra that we know and that exists always, and we consider our order basis of L, then the Poincare-Birkhoff-Witt theorem tells us that how to write a basis of UL. That is actually our monomials, our words in the element of L, are ordered words in element of L. So, given that, if we consider, for example, the trivial Lie algebra, the easiest example we can do, then the universal enveloping algebra is actually the vector space generated by the unit. So it's isomorphic to the field. This is the only case in which the universal enveloping algebra is finite dimensional. In fact, if we take a one-dimensional Lie algebra, already the universal enveloping algebra is spanned by this basis, delta k, for k greater or equal to 1. And this is actually isomorphic to the ring of polynomials in one variables, the commutative rings. If we take a finite dimensional abelian Lie algebra with dimension D, then the universal enveloping algebra is again the ring, is isomorphic to the ring of polynomial in the variable. Okay, so now finally we can talk about, I can define the algebras with derivation. So from now on, for me, A is going to be an associative alpha, F algebra, and L a Lie algebra with F. Then we're going to say that A is an algebra with derivation or a L algebra if L acts on A by derivation. So A is an L module, but the action of L is by derivation. So this means that we have there exists a Lie algebra homomorphism from L to the Lie algebra of derivation of A. Most of the time I'm going to identify the Lie algebra L, that is in general an abstract algebra. I'm going to identify with a subalgebra of the derivation of my algebra A. Okay. But this, by the universal property of the universal enveloping algebra, we can extend this Lie algebra homomorphism to an associative algebra homomorphism from the universal enveloping algebra UL of L to the associative algebra of endomorphism of A. Thanks to this, we have that any Lie algebra A is a right UL module. Right because I'm acting by, for me, the modular or by a right module. I'm acting from the right. So this comes from also from the Poincare-Birkhoff-Witt theorem. And also the Poincare-Birkhoff-Witt theorem tells us how we had by elements of our universal enveloping algebra that actually we are acting by the first derivation, then we are acting by to the result, we are acting by the next derivation, and so on. So, give some example. The first one, trivial action, the trivial example, almost trivial, that's not actually trivial. So I consider an associative algebra. I take any Lie algebra. I don't care about really the structure of L. Then I'm gonna consider the action of L on A as the trivial action. Just mean that the imagine of L is just 0, and I'm gonna consider then the action of UL in the action of UL on A. To understand how is the action, actually what we have to do, we have to see the kernel of our action of UL on A to understand which are the elements of UL that are acting non-trivially on our algebra A. Of course, since the action is trivial, the only element of UL that acts non-trivial is the unit. So acting by a trivial action means acting by the field. And this tell us, basically these are just an associative algebra. If I act by any Lie algebra by a trivial action on A, I get just A, the associative algebra A. And this tells us that any algebra A can be regarded as an L-algebra when L acts trivially on it. Okay, a less trivial example. So I'm going to consider now, we are going to consider the algebra of upper triangular matrices of order 2, and we are going to harden it by a one-dimensional Lie algebra, and in particular, the action is going to be the action of the adjoint of E22. And I'm going to call this algebra UT2 epsilon. Then, of course, we have to consider universal enveloping algebra. That is the universal enveloping algebra of a one-dimensional Lie algebra. That is the ring isomorphic to the ring, the commutative ring of polynomial in one variable, epsilon. And then I'm going to consider the action of the universal enveloping algebra on UT2. So now, again, we want to see who is the kernel. We want to determine who is the kernel of the action of UL on UT2 to better understand which are actually the derivation or composition of derivation that acts in a way that is not trivial. So we're gonna add, we take a generic matrices of UT2, we add by epsilon, and we basically get the corner, just the corner. And if I add again by epsilon on the result, I'm gonna get again the corner. What this tell us? This tell us that if I apply 2 times if I apply epsilon square or epsilon is the same. And this tell us that the kernel of my action is actually the two-sided ideal generated by epsilon square minus epsilon. And so this tells us that the derivation that acts in a way that is, let's say, non-trivial are just 1 and epsilon for this algebra. Now let's see the algebra in case let's see in case M is equal for matrices of order 2, sorry, and we are going to consider the action of SL2. We are going to consider the action of this fully algebra of derivation. Then if we fix, as I told you, I fix the basis of SL2 be this one. E is the adjoint of E12, F is the adjoint of E21, and H is the adjoint of E11 minus E22. Then again, we construct the universal enveloping algebra, that is infinite dimensional associative algebras. I consider the action of UL on M2, and then again, which is the kernel of this action? It's to understand better the action by derivation. Jose Brox and I, this year, a paper that you can find in archive, actually proved that the kernel of this action is a principal ideal generated by this element, where omega is the Casimir element. Okay, So, in particular, if you do some calculation, we can see that the elements of the universal enveloping algebra that acts on M2 in a way that is not trivial are just this one. So are the unit E square, F square, H square, E half, EH, and FH. Okay, so now finally we can talk about our symbolic expression, our identities that are called differential identities. To do so, we have to first define what are the differential polynomials. We consider now L-algebra L-algebra L, sorry. Then we consider its universal enveloping algebra with a fixed basis. Then we can construct, we can consider this tensor algebra. That is the tensor algebra of the vector space generated by the countable set of non-commutative variables, tensor the universal enveloping algebra UL. Then this algebra is the free associative algebra with this kind of free formal generators. Instead of using the tensor, I'm going to use this exponential notation. We can see that this algebra is consisting words in this kind of words that we have in exponent element of UL, and the multiplication is just the juxtaposition. Actually, this algebra has a structure of L-algebra by defining an action of L in this formal way. It's a formal action, understanding it by the Leibniz rule. And then it's like we can prove that this algebra is actually satisfied its universal property. This universal property basically tells us that this algebra is a free object in the class of L-algebras, of algebras with derivation. So actually, we call this algebra free associative L-algebra. And the element of this algebra are the so-called differential polynomials. So basically, differential polynomials are non-commutative polynomial in which the variable have as an exponent element of the composition of derivation, let's say so. So if I consider an L-algebra A, then a differential polynomial is a differential identity for A if it vanishes under all the substitution of variables by element of A. We are going to do this identification to simplify the notation. So when the exponent is just a unit of the universal enveloping algebra, I simply don't write it. So if I consider UT2, the algebra 2 times 2 upper triangular matrices with any L action, then this differential polynomial is a differential identity of UT2. Why? Because the commutator of any two upper triangular matrices is a matrices of the type E12, and so the product of two commutators is 0. Notice that we have to notice that actually in here there are no derivation. So this actually is just a non-commutative polynomial. So this is just a polynomial identities of UT2. And actually, any polynomial identities of an algebra, it's a differential identities of the algebra. Let's see another example, less trivial. So I consider again UT2 with my action by epsilon. So in this, we already determined the kernel of the UL action. And then an easy identity is this one, x to epsilon square minus epsilon. Why? Because if I take an element of the kernel of the action, of course, the action to any elements of UT2 is 0. So, of course, in particular, the generator of my kernel act to any element, send an element to 0. So this is a differential identities. A less trivial differential identities is this one, is the commutator to the epsilon minus the commutator is a differential identities of UT2 epsilon. Why? Because the commutator, as I said before, of two elements of UT2 is matrices of the type E12. And if I apply my derivation epsilon to an element of the type E12, the epsilon just fixes the element. So then we have this identity. Okay, an example for matrix algebra. So we already know this is a matrix algebra with SL2 action. We already know the generator of the kernel. As before, if we consider the generator of the kernel, then X to this generator is a differential identities for M2 with this action. But we have also other identities. So if I define this element, so row of the row E2 I2, row E12 E12, and row E12 E21. So there are linear combination of elements of UL. Then we have these three differential identities. Why these are differential identities? Because if, for example, we consider the first element, row E2 E2, I2 I2. This element, this linear combination of elements, act out on M2, basically send the identity to the identity. So if this, and all the other element is sent to 0. So of course, if I do a commutator, if I take a matrices and apply row E12 to it, I get just the identity part, let's say. So the commutator of this to any other element is 0 because it's the identity in the images. And similar reason also all this one, the third polynomial, is also a differential identity. Okay, so the main point in PI theory is to find the polynomial identities of a given algebra. In particular, if we are talking in the area of the differential identities, then we want to find the differential identities of a given algebra. So if we consider the set of all the differential identities of A, then this set is not just a set, it's a two-side ideal of the free L-algebra, and also is invariant on the endomorphism of the free L-algebra, so it's called the TL ideal. And we have also the converse, so any TL ideal is of this form. So finding the differential identities of a given algebra means finding the TL ideal of the free L-algebra. So basically the question, we can translate the question of finding the differential identities of a given algebra to the question, how we can determine the generators of the T ideal of an algebra A as TL ideal. Okay. I'm gonna present some example. First of all, we consider a trivial action. I recall you that trivial action means that we are actually just considering associative algebra. So the TL ideal, I'm gonna call just T ideal of ordinary identities of A. And we have some example of in which the generators were determined. For example, for UT2, we know Maltsev proved that the generators of the TLDL is just this polynomial. For M2, is this two polynomial. This is the standard polynomial of order 4, is like a high order commutative law, let's say so, and this other polynomial. But the big problem is that in general, to find the generators of a TLDL, so it's really an hard task. In fact, already for M3, we have no idea. So it's extremely hard to answer to this question. In the case of non-trivial action, we have some other example. So if we consider, for example, UT2, in a paper with Gian Bruno and another paper by myself, we actually describe the generators of the differential identities of UT2 for any L action. by derivation for any. So we have a complete result for a UT2 with derivation, and in particular for UT2 epsilon, this particular action by derivation, we have that actually the differential identities. The TL ideal is generated by just these two polynomials, the one we already determined before. In case of matrices, we have a surprising result for matrices with derivation, because in case the algebra of MK of matrices of order K with an action of SL K, so I am Brox in the Brox and I, we completely describe the T ideal of this algebra. We describe the generators. In particular, for M2, the generators are this one, the one I already showed you before. And this is a surprising result because we solve it for any K greater or equal to 2. Something that is still an open problem for ordinary algebra, for just associative algebras. Okay. Since to work with the polynomial identities and find generator is something really hard, in 1972, Regev opened a new way of studying polynomial identities that is a more combinatorial approach, and this helps us to have some quantitative information on the identities, because also if we know, even though if we know the generators of the T ideal, it's really hard to from the generators have information on the derivation on the polynomial identities of any order. So a combinatorial approach can help to have more information. So to define some function that measure in some way the growth, we have to consider the space of multilinear differential polynomial. There are basically polynomials in which in each monomial the variable appear all the variable at exactly one time. And since the field is of characteristic 0, we have actually that the differential identities of A are completely determined by its multilinear polynomial. So we can define the hand differential codimension of the L-algebra A be this non-negative integer. So it's the dimension of the space, the quotient of the space of multilinear polynomial quotient to the multilinear identity of A. We consider the quotient because this space, the multilinear polynomial identities of A, it grows really fast for n when n goes to infinite. So it's better to use the quotient; is easier. Of course, in case the action is trivial, we go back to the just associative algebra. And in this case, the codimension are just called, we don't have any more differential codimension, but just codimension. Okay? So some result, some example. In 1976, Latish have determined the codimension sequence for UT2. Ordinary UT2 associative algebra. Processi and Regev in 1984 determined the codimension sequence for M2. Processi determined this exact formula, and Regev proved that this is actually asymptotically equal to this value. For what concern algebras with derivation, Gianbruno and I determine the codimension sequence for UT2 epsilon, that is this. And Brotz and I determine the codimension sequence for MK for K for A greater or equal to 2. We have to notice that all these codimensions are exponentially, they grow exponentially. This grow like 2, this grow like 4, this 2, and this K. Well, And this is not just a random result, but actually is a pattern that is also that come from that has a really deep meaning. In fact, I'm gonna try to explain this differential because as I told you before, it's really difficult to determine the differential identities. So now the other problem is, okay, we don't know the differential identity of an algebra, how we can determine the differential codimension? So there is still a problem, right? But actually the differential codimension, they measure in some way the growth of the TL ideal of an algebra. They measure actually the co-growth, but I'm going to say just the growth for simplicity. And so in this setting, try to study the growth of codimension asymptotically. In 1972, Regev proved that in case we have just ordinary associative algebra, so the action is trivial, the L action is trivial, the codimensional sequence is actually exponentially bounded. And so the result we said before, some slide before, they are all exponentially. It's not this result. This example confirmed the result in some way. Kemmer proved something more in 1979 that the codimensional sequence is exponentially bounded or grow polynomially. So there are no intermediate grow. So we have or just polynomials or exponentially growth. And actually, Jambrun and Zaitsev in 1999 proved something more. They proved that there exists this limit. So it's the limit of the hand root of the codimension sequence. And this limit is a non-negative integer. And it's called exponent of A. This limit tells us that actually we now have a sort of integer scale, and we can try to study the algebras, the polynomial identities, depending on their exponent. So we can fix an exponent 2, 3, 4, 5, and we can try to study for this exponent what kind of algebras we have, etc. For what concerns the codimension of the differential codimension when L acts non-trivially, we have a result by Gordienko of 2013 for L-algebra, finite dimensional L-algebra, and he proved again this limit exists. And it's called the L exponent. So again, for L codimension, we have this integer scale. And as a consequence, of course, again, even for differential codimension, also for differential codimension, the growth is of the codimension is either the codimension are either polynomially bounded or grow exponentially. So as I told before, I say it several times, we can always see the ordinary polynomial as special case of differential polynomial, and in particular, if we talk about our multilinear polynomial, the multilinear polynomial ordinary one, Pn is the ordinary multilinear polynomial, how actually we can see them inside the multilinear polynomial, differential polynomial, and this tells us that actually these two spaces are equal, and this tells us that the ordinary codimension of A, so are actually less or equal to the differential codimension of A. And as a consequence, the exponent, the ordinary exponent of A, is less or equal to the differential exponent of A. Okay. In 2014, Gordienko and Kochetov conjectured that actually these two exponents are equal for any finite dimensional L-algebra, and they and they prove it in case the L-algebra that is acting is a semi-simple L-algebra. I don't know what's happening. Okay. In 2022, in a paper with Dos Santos and Vieira, we proved that actually we extended this result and we proved that when we have exponent 1, the differential exponent and the ordinary exponent are equal. So for polynomial growth, they are equal. Again, okay. And last year, I proved an even more general result that for any L-algebra, actually this conjecture is true. Then the exponent, the differential exponent, the ordinary exponent are actually equal. This is quite, again, sorry. This is quite surprising because in general, when we consider algebra with other additional structure, this is not true. However, we have to be careful because even though the exponent is equal, this doesn't mean that, again, this doesn't mean that the codimension are equal. This is just an example of the algebra have the same exponent, but the codimension are not equal. It's the same algebra one times is the ordinary one, and this is like C as L-algebra. Okay, so since different algebras, L-algebras, can have the same differential identities. So it's better to talk about more in detail about growth. So differential identities is better to translate our definition of a result in terms of a variety of algebras. So I'm gonna consider the L variety generated by the L algebra A, that is basically the set of all L-algebra that satisfy all the differential identity of A, and maybe some more. And sorry, again, I have some problem in the computer. Okay. We are going to define, we are going to say that the variety generated by A has a polynomial growth if the codimension sequence of A is polynomially bounded. And we're going to say that the variety has almost polynomial growth if the codimension sequence is not polynomially bounded, so grow exponentially, but every proper subvariety has polynomial growth. So in some sense is minimal, okay? When we had with the trivial action, again, we go back to the ordinary polynomial identities, and then the variety generated by A is just a variety of associative algebra generated by A. Okay, for variety of associative algebras, Kemmerer in 1979 proved that the variety generated by UT2 has almost polynomial growth. In few years ago, in a paper with Gianbruno, we proved that actually, if we consider UT2 with the non-trivial action by epsilon, then again, this algebra has almost polynomial growth. So grows exponentially, we saw it. I present the codimension sequence. The growth, the exponent of this algebra is 2, and but every proper subvariety as polynomial, the codimension sequence is polynomially bounded. But we have to be careful. UT2 is with this derivation, with the derivation epsilon as almost polynomial growth. If we consider other of their action by derivation, not always as almost polynomial growth. And actually, if you consider the action by delta is the derivation induced by E12. This has no almost polynomial growth. Okay, so the almost polynomial growth depend on the action of the Lie algebra. Okay. But in a paper of last year, I proved that actually just UT2 and UT2 epsilon are the only finite dimensional L-algebras generating variety of almost polynomial growth. So as finite dimensional algebras, we don't have any others that are generating variety of almost polynomial growth. But we have to be careful because this is true for if L is a solvable Lie algebra. So if I had by a solvable Lie-algebra. In fact, if the Lie-algebra is not solvable, this is not true. And Brooks and I, we actually proved that the variety of L-algebra generated by MK with the SLK action, that is basically the derivation, the action of its full algebra of derivation, has almost polynomial growth for an EK greater or equal to 2. This is really a surprising result, because MK in the ordinary polynomial has no almost polynomial growth. Absolutely not. Because in a variety of MK, we always can find, for example, UTK, so the 2k times k upper triangular matrices, and they have no polynomial growth. So this is really surprising. But these are not the only algebras. If L is not solvable, these are not the only algebras with almost polynomial growth. In fact, if we again, sorry, I don't know. Oh, it's here. So, in fact, if we consider as L-algebra SL2, so my Lie-algebra SL2, and then we consider MK with an action of SL2. I'm not gonna explain in details this action, but it's a sort of generalization of the action of SL2 on M2 by considering the irreducible representation of SL2 of dimension M. And then we consider the irreducible representation of SL2 of dimension M plus 1. Then we can consider this other algebra, UT2 of Vm, that is this basically in here we have the field, and in the corner we put element of the irreducible representation. Then these are natural SL action, where I act by SL2 just in the element in the corner, so in my irreducible representation of SL2. And then Argenti, in a paper of this year, proved that MK with SL2 action for k greater or equal to 2, and these algebras UT2 of Vm are the only finite dimensional SL2 algebras generating variety of polynomial growth. So already for SL2, we have, when we act with the simple algebra SL2, we have an infinite family of finite dimensional algebra generating variety of almost polynomial growth. So when we act with simple algebras, or the things are like, they kind of explode. So we have a lot more algebras generating variety of almost polynomial growth. Sorry, again. What this result of almost polynomial growth tell us about the polynomial growth of varieties. So if we consider a finite dimensional L-algebra, then the following conditions are equivalent. So of course, if the codimension sequence is polynomially bounded, the differential codimension sequence is polynomially bounded. If and only if the differential exponent is less or equal to 1, if and only if the ordinary exponent is less or equal to 1, we prove that they are actually the same. And this tells us that if and only if the ordinary codimension sequence is polynomially bounded. Then, in case L is solvable, these conditions are also equivalent to say that UT2 and UT2 epsilon, they don't belong to the variety generated, the L variety generated by A. So in case of L solvable, we have this. In case of L semi-simple, instead, we have we have a long list of algebras, because these are two classes of infinite dimensional L-algebras. These are sort of generalization of what I explained before, I show you before. And all these, and Argenti in a paper of this year proved that actually if these families of algebras don't belong to the variety generated by A, if the differential codimension sequence is polynomially bounded. And that's all. Thank you.
Thank you very much, Carla. Let's see if there are questions.
Well, maybe I can ask a naive question. Hi, Carla.
Hi.
Can I ask a question, Mikola?
Yeah, of course, you're welcome.
Okay. So, first of all, thank you for the very nice talk. Very interesting as usual. It's a naive question in a certain sense. It seems like an obvious stupid question, but well, I had it in my mind because I was confused at some point when you're saying that all the derivations of the upper triangular 2 by 2 matrices were inner, and I thought that was not correct. And then I realized that that it is correct. What I was thinking was wrong, because if you think of it as a Lie algebra, then it's not true. Then you have outer derivations. So my question is, since in that example you were using inner derivations, a pre-question would be, does it make a difference when you consider outer derivations? And the other question would be, I suppose you can make all of this work instead of using instead of having a Lie algebra acting on an associative algebra and looking at the L-identities, at the corresponding differential identities, you can have a Lie algebra act on another Lie algebra and look at the identities in that context. So I don't know if there's anything interesting that you can say about one of just pick one of these two questions, let's say.
So the first question was about yes, UT2 as associative algebra, as all the derivation are inner. And your question about this was
can you detect some different behavior when you're looking at differential identities when the differential parts of the Lie algebra part is acting as outer derivations, so derivations which are not inner? And
okay, in terms of growth, no. In the meaning, for example, the exponent, the exponential growth of the codimension sequence, so of the differential polynomial, is exactly the same of the ordinary exponent, even when we had with outer derivation. It's always doesn't depend if they are inner or outer. It's always true. So in general, I would say no. It's not depend on the inner or outer. It's dependent on the real action and the structure of the Lie algebra itself. It's more this to the two important things. About the other question, yes, you can work in Lie algebra acting on by derivation Lie algebra, of course. It's an interesting question, and I've never worked on it. I don't think there are results on this so far. So far, there are some general in the meaning of the growth, like of the exponent, the codimension, but not actually determining TADL of the generators of TADL, or this more concrete example. There are none. So it's an open question. There is a lot of work to do in this field.
Okay. Thank you, Carla.
You're welcome. And any question, all the questions are always interesting. There are no questions stupid.
Okay.
Okay, thank you. More questions? Well, so thank you, Carla, once again for your nice talk, and thanks for all the participants for your attention, and wish you all a nice week, and see you all next Monday.
Thank you very much again. Bye.